In this lecture, we will be deriving the regression normal equations, which will be the analytic solution to our multilinear regression problem. So first, let's remind ourselves of our multilinear regression model. So we have our observations of the vector of predictors and the response variable. So we have n of these. And this is the relationship that we have between them. And what we want to do now is vectorize this problem so we can use our knowledge of vector calculus to solve this regression problem analytically. So first, we want to reorganize this problem. And so let's define first a matrix X. So we'll just write it as a large X to indicate that it's a matrix. And we write this by essentially lumping all of the information from the predictors into a matrix. So for the first row, we will have the first observations across the P predictors. And we're going to need a constant 1 there, which we will see in a second, to pick up the intercept of the model. But again, this row represents the first observation of each of the P predictors. Then the second row will be the second observation for each of the P predictors. So the first subscript will change from a 1 to a 2. And then we go all the way down to the final observation, which is the case where the first subscript is n. And so think of this as a very tall but thin matrix. We'll have fewer predictors, P, than we do observations n, typically. So there are many more rows than columns. We then lump our observations of the response into a vector. So we'll have y1, y2, down to yn. And we can also put our beta coefficients into a vector, beta naught, beta 1, down to beta p, and our noise terms into a vector, epsilon 1, epsilon 2, down to epsilon n. And we now have all the tools that we need to vectorize this problem. And by that we mean this defining equation here, this is the case for the general ith observation, but we will now incorporate n of these equations into one system. And we do that by saying the vector of observations y is equal to this matrix X times beta plus the epsilon vector. And we can check our sizes of these to make sure the matrix vector multiplication works out and the addition works out. So y is an n by 1 vector of observations for the response. X has n rows and p plus 1 columns. Beta is a p plus 1 by 1 vector, and epsilon is an n by 1 vector. And so we see this matrix vector multiplication results in an n by 1 vector. So we have an n by 1 equals an n by 1 plus an n by 1. So this makes sense. And we can see this ith equation coming out of this expression. So the ith entry of y will be the ith row of x dot product with beta plus epsilon I, which is exactly what we have here. So this equation captures our entire regression model for all of the observations. So we now have this. And we now want to look at our least squares problem. So our least squares problem, we can think of it as rewriting this expression here as epsilon equals y minus x beta. And so these, the terms in the right-hand side, are the errors, or they're going to be the estimates of the noise terms that we're trying to minimize. So just think about what this vector actually looks like. This is the ith entry of this vector is the ith observation minus the ith fitted value. What we want to do is minimize the sum of the squares of those errors. Well, what does it mean to take a vector and take the sum of the squares of its entries? That is nothing more than the norm, the 2 norm, of y minus x beta squared. So our problem is to minimize over our choices for beta. So beta lives in Rp plus 1. This 2 norm. And again, if we want to see explicitly what that is, that's the sum I going from 1 to n of the squares of that I fitted value minus what we have from our regression equation. Beta naught plus beta 1 times x I1 plus beta 2 times xi2 up to beta p xip squared. Now we know we can rewrite the square of a 2 norm of a vector in a clever way. So if you have a vector, say y, and we look at its 2 norms squared, we can write that as the dot product of y with itself. And so we use that here to rewrite our optimization problem in this way. So our regression problem becomes minimize over beta in Rp plus 1 the 2 norm squared, but written as y minus x beta transpose y minus x beta. So the 2 norm squared of y minus x beta is rewritten as this dot product of y minus x beta and itself. And this sets us up nicely because we can rewrite this. So first we know we can distribute the transpose in the first term, and so we get y transpose minus beta transpose x transpose times y minus x beta. And we can then FOIL out this expression. So this will be first y transpose y. Then the outer, we have minus y transpose x beta. Then for the inner term, we have minus beta transpose x transpose y. And then the outer term, we get plus beta transpose x transpose x beta. We then notice these inner terms can combine. So let's think about the dimensions for these products. So beta is a p plus 1 vector. So beta transpose is 1 by p plus 1. X transpose, so x is n by p plus 1. So X transpose is P plus 1 by N, and Y is N by 1. So this product is a 1 by 1, or a constant. In fact, each one of these terms is a constant. But the reason why this is handy is that since these two middle terms are constants, we can replace one of them with its transpose. So we now note, if we take the transpose of this term, we get beta transpose, X transpose, Y transpose transpose. And we see that this term and this term are in fact the same. This becomes, thus, Y transpose Y minus 2 beta transpose X transpose Y plus beta transpose X transpose X beta. This means that our objective function, f of beta, is equal to this expression here that we just derived, and this is a convex quadratic. It's a convex quadratic because it's a least squares problem for a linear regression, or another way you can look at it is it's the 2 norm of a matrix. But if it's convex quadratic, that means the first order conditions are necessary and sufficient for a global minimizer. So if we set up our first order conditions with specifically the gradient of f of beta being equal to the 0 vector, we can recall from our knowledge of vector calculus how to compute the gradient of this with respect to beta. So first of all, we know that no beta appears in the Y transpose Y term, so that will not contribute anything to the gradient. Here, we have minus 2 beta transpose times this vector, which means the gradient for this term will be minus 2 times the vector multiplied by beta, which is X transpose Y. And then here, we recognize this term as a quadratic form with coefficient matrix X transpose X. And so we know that the gradient from that term will be 2 X transpose X times beta. We thus have our first order condition being X transpose Y equals X transpose X times beta. And if X transpose X is invertible, we have beta, our beta hat, multiplying both sides of this equation on the left by X transpose X inverse, we get X transpose X inverse times X transpose Y. Now the requirement that X transpose X being invertible can be thought of in the following way. Remember that X is N by P plus 1. So X transpose is P plus 1 by N. So X transpose X is a P plus 1 by P plus 1 matrix. That is not a large matrix compared to X itself. Remember, typically P, the number of predictors, is much smaller than the number of observations N. And this will result in a invertible X transpose X if X has full column rank. So this exists if X has that full column rank, which really results from the predictors not being dependent on one another. So typically you will see this. And this equation here is what we call the normal equations for our linear regression. Now we do give a name here for some of this. And we give that name when we rewrite this in terms of the actual fit. So our fitted values for our regression can then be written as y hat equals x times beta hat. Right? Let's go back to our original vectorization of the problem. Once we have our fitted values, that y hat equals x times beta hat gives us this expression here for all of the observations, with the betas replaced with their estimators, and we lose the epsilon I. And now if we plug in for this beta hat expression that we have x times x transpose x inverse x transpose y. And this expression completely captures the solution to our multilinear regression model analytically, as long as we have a full column rank for our matrix that has all of the predictor information. And so we rewrite that here. And we note some standard terminology. This matrix, everything that's multiplied on the left of y, we call H, or the hat matrix. And so this regression is written as that hat matrix H times the vector of observed responses y. And we notice that that hat matrix, it has all of the information in the observations of the predictors built into it to give us our regression result. And this becomes important later on because the hat matrix is used to develop some concepts like leverage in terms of actually looking at the effect of outlier points in the data set. But this really gives us a nice expression, a nice way of writing down analytically the solution to our multilinear regression model. And this comes in very handy when you need to do different algebraic manipulations when working with multilinear regression.